Okay, so what we're going to do now is talk about Java synchronizers. We'll talk about some of the language features that are available in Java that do synchronization, and we'll also talk about some of the library classes that are available in order to be able to help synchronize threads in concurrent programs. We'll start by giving an overview of what synchronizers do. So Java's synchronization mechanisms address various inherent complexities in concurrent software. And inherent complexities are complexities that are really the fundamental challenges of what we're doing, as opposed to accidental complexities, which arise due to limitations with languages or tools that we might use that are out of date or obsolete. Some of the things that synchronization does is help to ensure that the interactions between computations don't corrupt shared data. That's one of the key things. And also make sure that the interactions between threads and computations occur in the right order, at the right time, and under the right conditions. And I'll talk more in a second about what I mean by each of those things. So I like to think about this stuff, sort of visually, and think about people dancing or something like that, where they have to synchronize their interactions so they don't step on each other or fall down or trip or whatever. One of the things that are important with respect to synchronization is ensuring mutual exclusion. And mutual exclusion, as we'll see, really deals with several different properties. One property is what's called atomic ordering, and that's making sure that operations are going to occur all at once or not at all. So a couple examples that I think of when I think about atomic ordering. I think about using a restroom in an airplane where you want to make sure that there's one person in there at a time. Or I think about, when I think about atomic ordering, I think about the transporter from Star Trek, where you either want to be in there and beam down or not. For those of you who are Harry Potter fans, the concept of disapparation is sort of an all or nothing thing. If you recall, if you read the books, they talk about splinching, which happens when you partly disapparate and then part of you stays behind, right? So that's bad. So atomicity means all or nothing. With respect to the kinds of things that we care about here, this really involves operations on fields that are shared between threads. So if you take a look at this example here, if you can see it, basically what we have here is we have two threads that are sharing a common field, which happens to be a long in this case. And what's going to happen here is that thread 1 or thread 2, doesn't really matter, the field starts out initialized to 0. Thread 1 reads the field, and then it increments the field by 1, and it writes the result back. And only then can thread 2 come along and read the field, increment the field by 1, and write it back. So this particular sequence of events would be considered atomic, because we're not doing a partial read or a partial write of that field while someone else is looking at it or modifying it. We'll take a look at some examples when that isn't the case in just a second. So that would be an example of atomicity. If you're using primitive Java types include things like longs, ints, shorts, and so on, or characters, or chars rather, then you don't get atomicity out of the box with respect to things like incrementing the values. You have to do something else. You have to use synchronizers somehow, as we'll see shortly. Another thing that we're trying to do with atomicity, with mutual exclusion, is avoid race conditions. And you may recall before, race conditions occur when a program depends on the sequence or timing of threads for it to operate properly. I'll show you some examples in a second of where race conditions will get us into trouble. And you'll see this is a very, very common problem in concurrent computing programs. So here's an example of race conditions that can occur with so-called read-write conflicts. So as you can see here, now that it's visible, if we have one thread reading while another thread is writing concurrently to the same location, then the field that's read may be inconsistent. So you can see here we have two threads, thread 1, thread 2, they're sharing this long field, starts out initialized to 0. Thread 1 reads the field, increments the field by 1, and then at the very same time, thread 1 writes back while thread 2 reads. And the question is, does the read of thread 2 read a 0 or a 1? And it all depends. It's a race to see who gets there first, right? If this value gets written back, then it'll read a 1. If this thing is not written back yet, when it goes to read it, then it'll get a 0 or something worse. So we talk about operations conflicting if at least one of them is a write. So this is called a read-write conflict, and that would be an example of a race condition that could occur because we're not properly synchronizing access to that shared field. Here's another type of race condition. This is the so-called write-write conflict. This occurs if two threads try to write to the same field concurrently, and the results may be inconsistent. So similar scenario, we start out with a long initialized to 0. We read from it in thread 1. We read from it in thread 2, so they both have zeros. Thread 1 increments the field by 2. Thread 2 increments the field by 1. And then they both write back at the same time. And the question is the value 1 or 2? It depends. It's a race, right? So actually, whoever gets their second wins, because whoever gets their second, their value will be the one that sticks. So these are some examples of race conditions. Now, they seem very simple, but you'll see as we get more advanced and more involved that these kinds of things can occur for all kinds of stuff, not just simple reads and writes of longs. The reason why this can happen, without getting into too much of the hardware details, which is a bit beyond the scope of this course, is because in multiprocessor systems, especially multi-core multiprocessor systems, to get the hardware to work as efficiently as possible, the hardware and the memory management mechanisms typically use what's called weak memory ordering. And I'll give you a couple of examples of weak memory ordering in a second from everyday life. But the way to think about this is that when you've got caches, then oftentimes the way the caches are managed and flushed back to the main memory that they're caching, it may end up with out-of-order operations for loads and stores, where it becomes somewhat non-deterministic what values you're going to get unless you do some other stuff, like use the synchronizers we're going to talk about. So it may turn out here, for example, the NV means non-volatile. That means things that can be stored in cache memory. So in this case, we're going to start out with main memory in some unknown state. And we've got a cache over here. And notice that this thread has written the value 7 to the non-volatile field, which is just a cache of this one. This thing doesn't know that this is being cached this way. I mean, it could if it thought about it, but it just thinks it's accessing an int or a long or something like that. So it's going to write 7. This guy's going to write 42. And the question is, when this guy reads, what value will he get? Will he get 7? Will he get 42? It's really hard to say because of the way that the caches work. And even if this thing gets written ahead of that one, it might turn out in terms of temporal time, like let's say at time, global clock time T1, this guy writes NV equals 7. And at global clock time T2, thread N writes NV equal 42. Just because one occurred earlier in clock time doesn't mean that the caches get propagated in the same order. And that's what's called weak memory ordering. Now, thinking about what you do in everyday life, right? There's lots of things you do in everyday life that don't follow the order in which the work was scheduled. So if you used your email inbox as a work queue to keep track of things like assignments or projects or papers or whatever, one way to handle it would be everything that came in the queue, you do it in exactly that order. That would be sort of strongly ordered. But in real life, we typically don't do that, right? We optimize for things like, when is the deadline? It doesn't really matter when it shows up. It's when is it due? Or what can I do very quickly because I have a few extra minutes between classes? I'll do that thing first. I'll do the shortest work first. Or I might do the thing I think is most interesting to me. So the way that you order your life isn't always in strict linear FIFO order in the order in which things showed up. And hardware is the same way. They come up with all kinds of ways to optimize behavior by reordering the instructions. And because of that, you can have these out-of-order issues. And so what we're about to talk about is ways of addressing this. So mutual exclusion is one reason or one mechanism that synchronization provides for you. The other thing that they provide is our coordination. So they coordinate multiple threads to ensure that computations run properly. And there's a couple of different things to think about with respect to properly. One way that things can coordinate to run properly is to make sure they run in the right order. So if you had a program that played ping pong, like the old video game Pong, you would want to ensure that if you had two threads, they would take turns doing ping and pong and ping and pong. And you wouldn't want one thread to go ping, 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 and then another thread go pong, and then ping, ping, pong, pong, pong. You want to do ping, pong, ping, pong. So synchronization can be used to coordinate the behavior of the threads to make sure that they run in the right order. That's one way they could coordinate. Another way they could coordinate is by making sure that they run at the right time. So temporal properties. This thing runs every 50 milliseconds, and then another thing runs at another 50 milliseconds or 20 milliseconds or whatever the time frequency or periodicity is.
Does it use a thread to synchronize other threads?
The question is, are threads used to synchronize other threads? Typically not. We would be using synchronizers, which is the focus here. And then another thing that we might want to do is to use synchronizers to coordinate threads is to make sure that they run under the right conditions. So if you think back to the Palantir manager application that we're using here, under the right conditions would mean when I get access to a Palantir, then I can run. But if I don't have access to the Palantir, I can't run. So I can control the order or the conditions under which things run by synchronizers as well. And there's other stuff, but those are some of the key ways in which coordination can occur. When we use synchronization properly and synchronizers properly, we can avoid various concurrency hazards, things that cause us pain and suffering in our programs. For example, we can use synchronizers to make sure that objects or classes have fields that have the right state, they have the right values that we expect, even when they're accessed or modified concurrently by multiple threads. So let's take a look at an example. In this case, a valid state means that each method preserves key invariants of the object or class. Let's say object in this case, an instance of a class. The class objects have certain invariants that need to be preserved. And so the methods have to preserve them. That's how we have programs that work properly. So here's a simple example. We've got an object that's going to implement a priority queue that ensures that the elements that are in the queue are always sorted in ascending order. So we want to make sure that irrespective of what threads are running and when they access this queue, that we're going to make sure that that invariant is always satisfied. Now, the key thing to remember about locks and synchronizers is that you have to make sure that these invariants are satisfied when the locks are not held. When the locks are held, or the synchronizers are held, in other words, you're ensuring mutual exclusion, then it may not be the case that the invariants have to hold. Because at that point, you have nobody else who can get in there and muck with them or read them. So it might be the case that while you're in the midst of updating the queue, either by deleting an element as shown here or adding a new element or whatnot, for that period of time when the queue is in flux, the invariants may not hold. But while the invariants don't hold, a lock has to be held or a synchronizer has to be held to make sure nobody can get in there and find the inconsistent state. Right? So it's kind of like an actor in a play. You know, they go and they change clothes between scenes. And as long as they can show up when they're on cue and deliver their lines flawlessly, you don't really care what they've been doing while they've been off stage, as long as they show up at the right time. And that's kind of the idea here. You've got to make sure that we use synchronizers to ensure these properties. There's something in Java called its memory model, which is an incredibly dry specification that you can read about here. And this defines the semantics of multi-threaded access to memory that's shared between threads, typically in a multi-core environment. Although it doesn't have to be multi-core, but it's typically in a multi-core environment. And this memory model defines the semantics of how the underlying virtual machine, the just-in-time compiler, the Java compiler, the processor core, blah, 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 can optimize the way in which the instructions run in the different threads in order to make them efficient without making them incorrect. So it turns out that you can actually, the underlying system can reorder things in memory to try to optimize the behavior, but you have to be careful that the memory model defines what optimizations are legal so you don't end up in a program that doesn't make any sense anymore. So let's take a look at some examples. So we would like to be able to rearrange the order in which things occur in order to maximize throughput in the memory bus, for example, the data caches and so on. And so we don't want these things to be overly restrictive so the hardware can optimize stuff. And as a result of that, if you take a look at this simple program here, if you don't put synchronizers in your code, it can end up that after running these two threads of control, thread 1 and thread 2, that share the shared state x and y, which both start out with the values of 0, it could turn out that after executing both of these threads, I equals 0 and j equals 0. Even though if you take a look at the code, it doesn't seem like it should be that way. So we start out, x and y are 0. Thread 1 sets x to 1, and then it sets j equal to the value of y. Thread 2 sets y equal to 1, and then sets I equal to the value of x. Well, because of the way that caching is being done inside the processor caches, the multi-core processor cache or caches per thread typically, or per core, it could turn out that this guy, when he reads the value of x, even though thread 1 has already modified it ahead of that read, that it will still have the old value of 0 in this processor cache. And so this is a perfectly legal outcome if you don't take any steps to the contrary to ensure that it's synchronized properly. Yes?
Why is x and y equal to 1 at this time?
Well, they're equal to 0. So the question is, why are x and y equal to 0? Is that your question? Why? OK, so what would happen here is that x and y get equal to 0. Both those values get cached in the two threads' processor caches. And over here, we set x to 1, but that's in the local cache of thread 1 that it's set. But over here, x is still in the cache, and it's set to the value of 0, which is what it started with. So when this guy goes to read x in thread 2, the value of x in the cache of thread 1 has not yet been flushed so that it will end up in thread 2's cache. And that's the whole point of caches. Caches are there to optimize things. And so they're going to be often going to be very aggressive in caching things. And so you have to be careful and use synchronizers if you don't want the behavior to be sort of arbitrary or undefined from your perspective. Another thing that a virtual machine or the underlying system can do is have program outputs occur in different orders and different ways. So here's an example of this. This is, again, very similar to what we had here before. In this case, we're going to store the value of x into register, value of y into register, and then we're going to go ahead and get the values out and so on. And we do not, the memory model doesn't allow arbitrary things to happen under these circumstances. So even if we rearrange the output, we don't want the values to be some incomprehensibly strange value, like 42, right? That wouldn't make any sense. The good news is you don't have to know all these details. You need to know that if you don't follow the proper patterns and protocols of synchronizers and monitor objects, which we'll talk about in a second, you'll end up with inconsistent results that are unexpected and hard to reason about. But in general, you don't have to be a memory model guru in order to write correct code, which is great. That's why a memory model exists, to basically define a contract between the people building the infrastructure software to make it run really fast and the programmers who are trying to write correct applications that do sensible things. So the rest of this lesson is going to talk about the language features and class libraries that we use to synchronize interactions between threads. We won't show a lot of Java code examples at the moment, but when we get further along, we'll show lots and lots and lots of them. Here are the categories of synchronization features and libraries that exist within Java. As you can see, there are 4 different categories. Atomic operations are actions that can happen all at once or not at all from the point of view of a program. It's like the transporter on Star Wars or Star Trek. You either transport or you don't. Mutual exclusion is used to prevent simultaneous access to a shared resource. So think about the restroom on a plane. You want one person in there at a time. We'll talk about that example later when we talk about synchronized statements, synchronized methods, and when we talk about reentrant locks. Coordination is what is used to ensure that computations in different threads run at the right time, in the right order, under the right conditions, and so on. And then the last piece here is something called a barrier synchronizer, or barrier synchronization. And this is used to ensure that threads have to stop at certain points, or a certain point, and can't proceed until other threads have reached the same point. And this is what's commonly used to coordinate the actions of many threads. The example I show here would be something from a horse race, where the horses can't start to run until they all get lined up at the starting gate. Or, I mean, think about, if you don't like horse races, think about sprinting in the Olympics or something like that, right? Whoever happens to be the first to get to the blocks can't start running, right? They'd win the race most of the time, but they can't do that. You have to wait till they're all there, and then they go, ready, set, go, psh, shoot the starter pistol. They all start at the same time. So that's an example of a barrier synchronizer. And we'll say that there's entry synchronizers and exit synchronizers, as well as other synchronizers for barrier synchronization as well. And then we're going to cover a bunch of different classes that are synchronizers that are part of Java. And you see we have about 9 of them or so that we'll talk about. These synchronizers are used very heavily in Java apps and in class libraries. And so you'll get a chance to see many examples, and we'll look at some of the code from Java and Android that implement all this stuff. as you'll see, when all is said and done, by the time we're done with the whole course, we will probably spend more time on synchronizers than we will on threading. Well, we will cover more threading, of course, because there's all kinds of more stuff to talk about. But threading is actually fairly straightforward. Starting things up isn't too hard. Coordinating things is what's hard. And just to give you an example from everyday life, this is a particular part of the world, but it could be Nashville traffic for all it matters these days. Does anybody know where this probably is? India. Exactly, right. So having been in India before, I can attest to the fact that that's what traffic looks like most of the time. So obviously, the hard part these days in India or almost anywhere is not getting a car and driving around. It's trying to coordinate all the cars and keeping them from smashing into each other. OK, so that's the end of part 1.